Right, I think we can begin in a minute. Just a moment. All right, so it's 7:10. We can begin. Good evening, everyone, again, and welcome to the second lecture in the three-lecture series on groups, symmetries, and gates theories and Lagrangians. I hope I'm audible. Can someone confirm?
Yep, you're on.
All right, thank you very much. So yesterday we talked about groups, and we saw what kind of groups there are, and we understood about what does a special orthogonal, the SO group, mean, what the unitary group, the U group, or the special unitary group, the SU group, and all mean. Today, we're going to be looking at some of their applications in physics, which is basically to understand what kind of symmetries arise out of them. This again is going to be a little bit mathematical, but I will again try my level best to make it understandable for the diverse crowd that we have here. So this is what we'll be covering today. The first is something called a symmetric group, which most of you are already aware of. But you may not have ever heard of them being called the symmetric group. And then we'll just look at what continuous groups mean. We won't be getting into the mathematical definition of it. And from yesterday's Lie groups and Lie algebra, we will continue the discussion and see what exactly are they. Right, that's about Lie groups and generators. And then we will look at symmetries for the groups that are required for the standard model, namely the O group, the U1, SU2, and SU3. Reason being, the standard model has an SU3 cross SU2 cross U1 symmetry in it. And then we'll briefly see what a gauge theory is, what does it mean for a theory to be called a gauge theory, and I'll give you a few examples of the gauge theories that have been working so well so far. All right, so let's get started. The first we're going to cover is symmetric group. All right, so what is symmetry? This is something that all of you are already familiar with, right? If I have the alphabet A, right, you can say that this is symmetric, because if I was to split it somewhere in the middle, the left half is the same as the right half, right? Or if I had a triangle, for example, right, again, if I was to split it in any of these directions, through this point, or through this point, the two halves that are being divided are the same, are identical. Right, so that's the idea of symmetry that all of us have, where the mirror image is the same as the original object itself. Or for example, the letter M, if I was to put it in front of a mirror, you still get the same M, right? So on and so forth. So when you translate that entire thing into a mathematical notation kind of a thing, you have symmetry to be some set of features or some rules that make sure that your whatever system you're considering is the same after performing some transformation. So in my mirror example here, this is called a reflection. Quite obvious, right? You have a mirror and you're looking at the reflected image, so that's a reflection, right? And based on these, you can class. So again, now we'll get into a little bit mathematical notation. Based on these, you can differentiate the kind of symmetries you have in terms of groups or in terms of transformations. The first one is called a continuous transformation or a continuous symmetry. And that implies an example for that is the rotation of a circle. So if I have a circle with a center over here, no matter how I rotate it, it's still going to remain the same. If I haven't labeled any points or anything, no matter how much I rotate it, it's still going to appear the same. Or it can be discrete, like the square. You will realize that the square is being rotated when it is being rotated, right? If you have a square like this, half a rotation would be something like this, like a diamond shape, and then another rotation gives you back the original square. And so it happens in steps, but for a circle, even a little bit of a rotation would still keep that circle as a circle itself. Right, now when we get into the mathematics of this, continuous symmetries can be studied using Lie groups, which we've been dealing with yesterday, whereas discrete symmetries can be studied using finite groups. Now, they're again a different kind of group set, which I will not be covering here. What we'll be dealing with in today's lecture is all about continuous symmetries, and therefore we're going to be covering about Lie groups and their generators and so on. Now, here are a few examples that you're already familiar with in terms of symmetry. You can read it, probably later on. All right. Now, symmetries can be local or global. What we mean by that is, let's say I have a space here, a random space, all right, and I consider 2 points right here. Okay. Now, let's say I put a coordinate axis on this, like so. We have, let's say this 3-dimensional. It doesn't really make a difference. Now, if I apply some transformation here, let's call that transformation to be some blue t, right? If I apply a transformation on this, and if that somehow affects the green one, through the green, if it affects the one circled in yellow, right? That's called a global symmetry, because no matter what you do, it affects everything, and in the end, the whole action, the whole transformation that you're doing, leaves your system invariant. It's like the thing that you do at one spot applies to everything, and your entire system is changed by the same amount. And in the end, it's an invariant system. It doesn't actually change much, like the circle that we have, right? In other terms, a global symmetry means there is symmetry at all points in space and time. All right. Now let's look at local symmetries. This is a bit more important to us physicists. Again, let's consider a space and the same 2 points and the same coordinate axis. If I apply a transformation here, it does not affect a transformation that I apply here, right? So if I have some invariant quantity that I want to study, then if I call this transformation T1, and if the invariance has to be satisfied for invariance, T1 and T2, where T2 would be the transformation I apply on this spot, are different. Right? So the transformation I apply at one spot on my left-hand side will be different from the transformation that I have to apply on the right-hand side, only to preserve invariance. Whatever it is that I'm studying, if I want it to be the same throughout my space and time, then I have to apply different transformations at different points in space and time in order to make sure that whatever it is, like distance or displacement or whatever it is that we're studying, remains invariant. Right? Okay. So that's about global or local symmetries. And as I said, we're going to be studying more about continuous symmetries, and those are understood by continuous groups. And it's nothing complicated, really. Continuous groups implies whatever it is that you're doing. Your transformations are just continuous in nature, like the circle rotation example that I gave you of. We just try to put it in a mathematical notation. The rotation that we did for the circle is a part of the rotational group or the orthogonal group O of n. This is something we covered yesterday. Let me switch to red. Yes, right. So this is the orthogonal group, or a group of all rotation matrices. And by extension, you also had a subgroup of this, which is the SO of n, the special orthogonal group, where the determinant, for a reminder, is equal to +1. So an element of the special orthogonal group has a determinant equal to +1. Now, like we had a complex analog of the rotation, which was a unitary group, we can by extension also tell about unitary rotations in a continuous group for continuous symmetries. And for our purposes of quantum mechanics and everything, we use the unitary continuous group. We use a continuous symmetry with the unitary groups instead of the orthogonal groups. But we also know that there exists a correspondence between SO3 and SU2. So, we're pretty good to go. It doesn't really matter if you want to prefer your real 3-dimensional space, or if you want to prefer your 2-dimensional complex space. It's up to you, right? Okay. The order is something that is important, and we will see why exactly is order important. So the order is defined as the number of parameters that you need to specify how you represent that group, right? And we'll see examples with this instead of trying to understand the definition for as it is. And it's because of these kind of groups that we have that we can, or the orders and so on for each of these groups, the ON, the SON, the SUN, the UN. It's because of these continuous groups and their orders is how we can define how many elementary particles do you need to have, how many fundamental particles do you need to have for any field that you're considering. And we will see examples of this again in the coming slides. right? So before that, a quick, intro to Lie groups and generators. Right. So, if you're reading the presentation, you can skip this, but I will just tell you what is going on here. We already saw that SON and SUN are Lie groups. You can go back to yesterday's presentation to read about what exactly happened and so on. Now, these can be generated by some quantities called the generators. We saw that for 3D space, 3D Euclidean space, it was like the I, the J, and the K, right? A rough example for any regular vectors that we have, right? And any vector in 3D Euclidean space could be represented as a linear combination of I, J, and K, and so on. Now, since we work with unitary spaces, because every field that we know, or the universe itself is quantum mechanical in nature, we deal with unitary groups. Or in general, any group that you have, any group U, not necessarily unitary for now, you can have a representation like this, where S is some generator, right? Where S is just some operator, if you want to tell it like that. But you can also put a mathematical definition that S is your generator for the group, right? And again, this might all seem too complicated. We will see examples of this later on. Right, this is all this. If you remember from yesterday's conversation, when we were understanding how unitary operators work in quantum mechanics, we proved the fact that if I had my unitary group representation as In minus I epsilon h, I'm sorry for the background noise, right? We had this where In is the identity matrix, right? From this we were able to prove that H is a Hermitian operator. This is a proof that we did yesterday, and we are sort of using that fact here, and using that and the representation we did here with this boxed equation. We can also prove that whatever your operator is, in this case, instead of H, we have S. It's just notations again. So what we can prove is S is also a Hermitian operator, which I have mentioned over here. S turns out to be Hermitian, which we showed in a previous section. And you can also find out that a unitary matrix has a determinant always equal to +1. And with that, you can determine that the trace of S is equal to 0. What do we mean by the trace is, if I have some matrix A, B, C, D, E, F, G, H, I, some random matrix, the trace of S is just the sum of the diagonal elements, A plus E plus I. That's the trace. Okay. And if S is Hermitian, if you consider this case, this is equal to 0. That's what we're trying to show here. All right. And the number of generators for a Lie group is equal to the order of the group itself. And order is something we defined over here. It's the number of parameters needed to specify its representation. So let's move on. All right. So now we get into the groups that are somewhat required for the standard model. The first one is the orthogonal group of n dimension. It's also called the circle group because you have a circle, let's say in 2 dimensions, and you have this, your axes, the x and y axis, but I'm not going to name them. Your rotation just works like so, right? You can just rotate it like this. So your axes also are somewhat rotated like so, and they are still perpendicular. The blue lines are still perpendicular and your circle is rotated, but it still looks like a circle. I won't be getting into the details of all of these, but SO3, as the name suggests, the n equals 3 implies it's a 3D rotation. You're rotating in 3 dimensions, and you're already familiar with those rotation matrices, the Rx theta, which if I remember correctly, goes something like this: 0 cos theta sine theta, 0 minus sine theta and cos theta. And similarly, you have Ry and Rz, and you can rotate your vectors or whatever you have in your 3D space using these operators, these rotation operators. Now, the dimensions or the order, this is also the order, right, of the special orthogonal and the orthogonal group is given by n times n minus 1 over 2. Okay. Now, if for SO3, let's, for example, we have 3 times 3 minus 1 over 2, that is 3 into 2 by 2, and the answer is 3. The order of SO3 is 3, and this is what we know to be I, J, and K vectors. Right? So you need 3 parameters, which is the I, J, and K in 3-dimensional space to represent any vector that you have. This is another way of saying why we have I, J, and K, and so on. Now, for 4 dimensions, it'd be 4 times 3 by 2, which is 6. So you need 6 independent parameters. So let me just write that down for you. SO4 would be 4 times 3 by 2, which is 6. Right? So you would need 6 parameters to determine any position in your 4-dimensional space. I won't be getting into the details of that, but yeah, it's just a rough idea to tell you how all of this works. All right. So yeah, like I said, your SO2 can be generated using poly matrices, poly spin matrices. You may or may not be familiar with all of this, but that's totally all right. Okay, and using that fact, and you can also find out how your 3D space can be represented in terms of the Pauli matrices. And like I said, you also have other generators, the Rx phi and Ry theta. These are also called the generators. This is what we saw here, right? These are sort of the generators, or because our elements of SO3 are supposed to be matrices and not just IJK, you represent them in the matrix form like so. Right? So you can go through all of this. But why do we do all of this is because it turns out that in your 3-dimensional space, whatever it is that you find out, these so-called generators, the Rx, Ry, and Rz, I don't know if I've mentioned Rz here. I haven't. Okay, that's fine. These rotation matrices that you find out, turns out that they can be related to the angular momentum of any body that you're considering in 3-dimensional space, and that's like a direct physical application of that. So I have not done the proof here because my aim here is to show you how these groups work, right? And the reason I won't be explicitly mentioning symmetry anymore is because these are symmetric groups. These are groups that preserve the invariant quantities, right? We talked about continuous groups, and the orthogonal group or the rotational group O of n is a continuous group. So by default, all of these preserve those symmetries and invariances that we talked about. Our purpose now is to understand how these groups actually function in the spaces that we, or in the scenarios that we have in physics. Right. So the next we're going to talk about is the group U1, which is unitary matrix of 1 dimension. Now, I won't be, again, getting into the details of all of this because, it gets a little complicated and you might lose interest pretty soon. But a few things that I'd like to mention is that the order of the unitary matrix is the U of n order is n squared, but the order of SON is n squared minus 1. So it's 1 less than that. And that minus 1 is because of this U1 rotation here. Right? Now, I will try to briefly explain to you what exactly is happening here. Not directly, but what's happening is in our complex space, we have the imaginary axis here and we have the real axis here. And let's say we have some complex number represented as so. All right. Now, this should be I theta. That's a typo there. Sorry about that. Now, the unitary matrix we saw back here, all the way back here, that we could represent, a relation, a generator, a relation like so, e to the I phi, where phi is a parameter. Similarly, in your unitary space, there's always a factor of e power I theta that acts on your elements of the unitary matrix or the unitary group. And what that does is it rotates your initial vector. So I'm going to give it names. If this was, let's say, A, right? I'll just call it A because that's a complex number. It rotates it to A prime, which is given by e power I theta A. It's just a rough example that I'm giving you. They're not matrices or anything. It's just complex number rotation that you're already familiar with. And this angle is theta. That's what is happening in our unitary spaces, right? That's exactly what's happening. Your complex numbers are being rotated, and we sort of try to exclude that one single rotation, which is isolated from everything else. Okay, and why exactly is that is a bit more complicated to discuss about, so I won't be talking about it right now. But what I want you to take away is how stuff works in the unitary space. All right. Now, why is the unitary group important in physics, at least, or why is a special unitary group important? Is because every quantum field that we know of is complex in nature. I have also mentioned this point in the previous session. Every complex field of the electrons, the quarks, the gluons, and everything else are complex valued, right? And even if we do think of rotations of these fields, we cannot apply our regular SO or O groups, because those O groups and the SO groups only have real entries in their matrices. But the unitary groups, the SU group or the U group, have complex entries in them, right? So in a sense, the elements of the SU group, let me switch back to red. The elements of SUN are matrices with complex entries, right? This implies they can perform what we would, generally call, what we'll generally call complex rotations. And the idea of complex rotation is like I showed you over here, right? It's just that. And that is why every symmetry that you have in the standard model or any quantum field theory is related to the unitary groups, or sometimes more specifically the special unitary group and so on. And again, yesterday we talked about there is the correspondence between the orthogonal group and the SU2 group, which is why you can shift them around, and whichever space you're comfortable working with, you can do that. That's it. So that's why we need a unitary group. We only talked about U of 1 here. We will move on and we'll talk about SU2 more specifically. So this is a special unitary group of the second order. Now, we talked about generators and stuff, right? So what we can do is we can find the Lie algebra, right, of the SU2 group. Now, what Lie algebra helps us find out is how you can evaluate the generators of your space. How exactly is the space being generated, and what is it that is generating the space? What elements are you using? We had I, J, K for the three-dimensional space. What is it for SU2? Because this is a complex space that we're talking about, right? There are and a complex number has a real part and an imaginary part that in turn have a real number and a real number, which is multiplied with a factor of I, which is the square root of -1. So the question we're trying to address here is how exactly is SU2 generated? And the answer for that is given by the Pauli spin matrices right here. And these are the Pauli spin matrices right here. Or sometimes they're just called Pauli matrices. You can call them anyway. They were derived from studying the spin of electrons. So that's why the name stuck on Pauli spin matrices, but they're just Pauli matrices in general. All right, and it is using these three matrices, the sigma 1, sigma 2, and sigma 3, that you can generate your entire SU2 space. And the reason they are matrices and not simple numbers like IJK is because the fact that we're dealing with matrix groups here. We're dealing with transformations. We're dealing with complex transformations on a complex space, right? And that is why these generators, these elements, the basic elements, are matrices in a sense. And from the previous lecture that was yesterday on groups, we can write the members as so. That's not important. And what you realize is there exists some commutation relation between them as so. So if you know any two generators, you can find out the third generator, which is either going to be symmetric or anti-symmetric. You can just figure out how it is. And why is SU2 important is because it describes the non-relativistic spin. Like I said, these Pauli matrices are derived from by studying the spin of electrons and how they behave and so on, by studying spin as a whole, right? So the SU2 representations, by studying SU2, you can understand about relativistic spin. And since there was a correspondence between SU2 and SO3, you can also understand about the rotation group in a regular three-dimensional Euclidean space, right? So, too complicated, doesn't matter. What is SU2? It is a group which helps you understand the spin of particles. That's it. And it also helps you understand the rotations in real 3D space. That's it. There's nothing else. Everything else is just mathematics. You can either go through it, not go through it. The only gist is about the spin and the rotation groups. That's it. Right. So this was again how SU2 was actually realized. I mean, why was SU2 required in physics is because when you were trying to understand spin, you had two states, the up state and the down state, which were represented by the vectors 1, 0, which was for up. So this is up spin, and this is down spin, represented as 0, 1. And it turned out that they were the generators for SU2. Like I said, they were matrices here. These matrices were again sort of derived from 1, 0, and 0, 1. You can go through quantum mechanics for all of that derivation. Right. And like I said, since there exists a correspondence between your unitary space and your rotational group, they were able to find out that there exists a relation with angular momentum, which has 3 dimensions. And so this again led to the correspondence that there exists every for every element of SO3, there are 2 in SU2, and so on. All right. The next and the last group that we're going to talk about is the SU3. Now, personally, I feel this is one of the most complicated groups to understand, but it's also one of the most beautiful symmetry groups that exists for us in standard model. We'll see what this is. It might get a little too complicated, but that's totally all right. All right. So in the previous SU2 here, we saw that the generators can be represented in terms of Pauli matrices. Now, the speciality with Pauli matrices, right, is that they are Hermitian, right here, and they're also traceless. This is exactly the condition we put forth right here. Right here, right? It has to be Hermitian, and it also has to be traceless. So any generator or any operator that you pick has to be Hermitian and traceless. And the Pauli spin matrices satisfied that condition. And therefore, we chose them to be the generators of the SU2 space. Does there exist a similar thing, a similar set of matrices for SU3? The answer is yes, right? But instead of just 3, you have 8 of them. All right. Now, why are there 8 of them here and just 3 of them here? The answer is for SU3 at least, you remember that the order of SUn is n squared minus 1. So for SU3, you have 3 squared minus 1, that is 8. And therefore, you have a set of 8 matrices that are required to generate your SU3 space. All right. And you can also work this out for SU2, which is 2 squared minus 1, that's 3. And those were the 3 sigma 1, sigma 2, and sigma 3 matrices. Similarly, you need 8 matrices here to generate your entire... Is my screen visible?
No, it just went off.
Yeah, okay.
No, just off.
Let me know if it's visible now. I think it was a small glitch.
Yeah, it's visible, Ikran.
Okay, I hope you can see this. All right.
Yeah.
So yeah, like I was saying, for SU2, you can work out the order, which was n squared minus 1. And for SU2, it's going to be 3. And that's why we had 3 Pauli matrices that were generating the SU2 space. Similarly, for SU3, when you calculate it, you have 8. And the answer to these 8 matrices are the so-called the Gell-Mann matrices, right? Named after the physicist Murray Gell-Mann, right? Now, before going further, I'd like to mention that these 8 matrices correspond to the 8 gluons. Okay, and it's a big leap. I do understand that, right? But these 8 matrices are the reason why you have 8 gluons in your standard model. All right. Let's just go through all of this. You can again represent a Lie algebra, a commutation relation, but one thing special. So this is a commutation relation for matrices. If you've studied a little bit of higher linear algebra, you would know what commutation relations are. But what's special about SU3 is it also has an anti-commutation, right? And the whole point of all of this, the fact that we're discussing there is some commutation, anti-commutation, there's 8 matrices and blah, blah, blah. All that tells us is the Su3 group tells us about quantum chromodynamics. That's how they're directly related to our physical concepts. They talk about the strong interactions. The Su3 group symmetry tells us about the strong interactions, and therefore it tells you about your quark gluon dynamics, how quarks and gluons behave, and flavor symmetry of lighter quarks and so on. We're not getting deep into the standard model right now, so I'll just tell you that the Su3 group corresponds to the entire field of quantum chromodynamics, right? So sometimes this is also called the color group. So you might see representations which says Su3C, or if you're dealing with flavors, then you might see Su3F and so on, right? But yeah, so Su3 corresponds to QCT, and that's a big discovery for which Gell-Mann won a Nobel Prize. This was the work of Gell-Mann. He derived all of this and he explained the whole field of quantum chromodynamics, and gave forth the whole gluon theory and so on, right? Now, all of you are already familiar with something called the Noether's theorem. If you've heard about it, it says that whenever you have some sort of symmetry, there is again some sort of conservation that is happening. If you've studied basic classical mechanics, you would have realized that linear momentum is conserved for translatory motion, right? So translatory motion here, or translation for in short, is the kind of symmetry that we're talking about. What that means is, if I have some system that has a path, okay, I'll call this T and I'll call this X, for example. Let's say I have some system that goes like so, right? If I was to shift this a little up, right? Let me draw that in blue. If I was to shift this a little up, nothing would change. There would be no difference. There would be no difference between the equation of motion for the red line or for the blue line. That's what conservation in a sense means, right? There is much more to this. Noether's theorem deals with the fields and everything. It deals with a quantity called action, the action integral that is defined over here. And this L is called the Lagrangian, which I'm sure most of you have heard about. It's called a Lagrangian, and in general, it's defined as T minus V, where T is the kinetic energy and V is the potential energy. For fields, the definition also remains more or less the same, but we'll get to that later, right? So when I say that this red curve and the blue curve are the same, what we're talking about is the action of these. Okay, it's a much deeper concept, which we will probably cover in tomorrow's lecture. But what I want you to take away from this is this relation here, that for every symmetry that you have something that is conserved, right? And it is because of this is why we have photons and the electric charge being conserved and the lepton number being conserved and so on. Right. So like I said, translations give us momentum conservation. Translation in time, if you change the time a little bit front and back, it gives you energy, because energy is something that doesn't change over time. So you call the energy to be a conserved quantity. We're talking about the total energy of the system, and that that is conserved because it doesn't change over time, right? So that's why there is that. Rotational transformation, like we discussed, right? SO3, you can relate it to the components of angular momentum. And therefore, a rotational transformation in your space-time conserves angular momentum. That's why we say angular momentum must always be conserved. We're talking about rotational stuff happening there. The next big thing that happened is that the electromagnetic field follows U1 symmetry, the unitary group of order 1, which we discussed briefly a few minutes ago. The electromagnetic field conserves something, and that something is the electric charge. Now, of course, there's a lot going on behind this, but what I want you to take away is there is, because of this U1 symmetry, electric charge is conserved. U1 is a symmetry group, like we discussed from the very beginning, continuous groups, and the rotational group was a continuous group. And again, a complex rotation is the unitary group, and therefore there is a rotational symmetry with the unitary group U1. And because of that, we have a conserved electric charge. I won't be getting into the details of all of this, but that's what I want you to take away. Right? The U1 group of the EM field gives us a conserved electric charge. All right. So that was about groups and everything so far. I have tried to make it as simple as I could. All right. So let's just briefly talk about the number of the orders of each group before we proceed to gauge theory. Right. So in the group U1, so the order of UN, let me just write it here. Order of U of n was n squared, and order of SU of n was n squared minus 1. Now let's look at the orders of each group that we've discussed. For U of 1, the order is 1 squared, that is equal to 1. That is the photon. That corresponds to the photon. Now for SU2, we have 2 squared minus 1, which is 3. That corresponds to the Z plus, the Z minus, and, it's the W plus, the W minus, and the Z0 bosons. So this is a boson. This is a boson. Now SU3 has 3 squared minus 1, that is 8. That corresponds to the 8 gluons, which are again also bosons. Right? Massless, massful, that is a topic of another discussion. But this is why you have exactly 3 or 4 gauge bosons and 8 gluons in your standard model and so on, right? But I just use the term gauge bosons. Where does that gauge even come in from? That's what we're going to look at next. And I'm assuming I still have around 10 minutes left, so yes, we can cover this. All right. So what's a gauge theory? You already heard the gauge several times, right? You're already familiar with the word gauge. You might have heard vacuum gauge or pressure gauge or something like that. It's just something used to measure something. Right? A pressure gauge is used to measure pressure. A vacuum gauge, again, is in some sense measuring a pressure and so on, right? Now, in physics, when you try to bring that idea to pure physics kind of a thing, a gauge theory is a field theory, right? It tells me about the fields where the Lagrangian, a quantity that we discussed in the action integral, that quantity called Lagrangian remains invariant. Okay, it does not change under local transformations. We also talked about what local symmetries are, right? So if I have a field here, right, a random field, and I have a Lagrangian at some point over here, let's call it L1, and I have another Lagrangian L2 over here, okay? Now a gauge theory, what it does is whatever transformation that I apply here, let's call it T1, this entire Lagrangian is to remain invariant. And if I want to study what happens to L2, I have to apply another transformation T2, okay? Now, what a physicist is interested is to study how are these two related, all right? And to do that, you sort of need some connection between them, right? You need something in between them to tell us how would one affect the other, even if they do, if they don't, or anything for that matter, right? I want that theory, whatever I have, the so-called gauge theory, to tell me what is going on. How can I study the transformations of one in terms of the other in a very vague sense, right? So yeah, any kind of transformation that you do here, in this case, T1 and T2 are called gauge transformations. T1 and T2 are called gauge transformations. And a set of all these transformations, you have a group, you can form them, you can make them into a group, and that will be called a gauge group. A set of all the gauge transformations and so on. And again, with this, like I said, you have something that is propagating, and like I said, it's a field theory. So you need a field And so for each generator that we discussed, the Pauli matrices, the gluon, the Gelman matrices and so on, you have a corresponding field called the gauge field. Everything, you just add the term gauge in front of everything and you have that. Transformation, gauge transformation, group, gauge group, field, gauge field, and so on, right? So that's what we have. All right, we have a gauge group and there is a corresponding gauge field for every generator. So this itself might give you an idea. For U of 1, we had one generator, right? So there's only one field. There is EM field. For SU of 2, we had 3 generators. So we have 3 fields, which was the field for W plus, W minus, and Z0 fields. Okay. And similarly for SU3, you had 8 generators. So you would have 8 fields, each corresponding to one gluon, or in general, the gluon fields, and so on, right? Okay. So like I said, we want the Lagrangian to be invariant, and whatever we do, we don't want the equations of motion to change. That kind of a condition under whatever local transformations that you're doing is called gauge invariance. Invariance we've been dealing with so far, something that doesn't change. And since we're dealing with gauge theory, you just add the term gauge in front of it and you have gauge invariance. You have gauge invariance right here. Okay, so I'll just read out to you what I've written there. In a Lagrangian for the field theory, whatever field you have, you can represent it in the form of a Lagrangian. And a quick recap, a Lagrangian can be represented as P minus V. Okay, the kinetic energy minus the potential energy. For a field, how does that make sense? We will probably look at that tomorrow. What do you mean by a kinetic energy of a field? What do you mean by a potential of a field? And everything is our topic for tomorrow. So yeah, now you can quantize these gauge theories. You can give them discrete values or something. Like we had 1 generator, we had 3 generators, we had 8 generators. You're able to quantify them, right? You can give numbers of generators that you have. So whenever you do that, whenever you're able to do that, whatever field that you're studying, if you're able to quantize it with the number of generators that you have, those quantities, the quantized quantities, are the gauge bosons. Okay, these are the photons, the W plus minus, the Z0, and the 8 gluons. That's why they're called the gauge bosons, because these are the results of quantizing your gauge theory for the standard model, which arose again from the symmetries that we had before, right? Now you can keep studying the properties of these so-called gauge groups, the symmetry groups that you have. And if the transformation is commutative, then you call it an abelian gauge theory. So let me just remind you what abelian is. An abelian group under addition, I'll just give you a simple example, is if A plus B is equal to B plus A, or in multiplication, right? That'll be A dot B, or A multiplied with B is the same as B dot A. The multiplication is commutative, right? So wherever it is, this commutativity holds, we call that group to be an abelian group. And if my gauge theory is made up of abelian groups, then I call it an abelian gauge theory. So in this gauge theory, the commutative law holds. That's basically it. And if it doesn't, then you call it a non-abelian gauge theory. That's as simple as that. All right. Now, a few examples. This is something that I've been telling over the past few minutes. Quantum electrodynamics, which is a quantized theory for electrodynamics, the theory of electricity and magnetism and electromagnetic fields and so on. When you quantize it, you find it to be an abelian gauge theory. And like I said, it already has a U1 symmetry, unitary group 1. The corresponding field is the electromagnetic field, right? And it's defined by the 4 potential. You don't have to know about that. But the quantized quantity is the photon, which is your gauge boson. So there you have it. I mean, you were able to understand what a gauge, I hope you've been able to understand what a gauge theory is and how exactly have we used it in stuff that we already know, like QED, for example. In short, this is QED, right? So our U1 group corresponds to QED. Okay, I'll write the next as we go along. The standard model, on the other hand, is a non-abelian gauge theory, which means the commutative law does not hold here, and we will try to address this issue in tomorrow's session on gauge theories and Lagrangians in a bit more detail. Okay, and like I said, it has a symmetry of U1, SU2, SU3. U1 is the electromagnetic field. SU2 is for the W plus minus and the Z0, also called the weak field, or the field for weak interactions. SU3 is for QCD, like we discussed. So let me just get rid of that so that it doesn't get too messy. Right. So like I said, the standard model obeys a U1, SU2, SU3 symmetry. And when you put all of these together, like right here, if you add these quantities up, 8 plus 3 plus 1, you have exactly 12 gauge bosons, which we have been discussing about so far. Right. So let's just take a quick look of what each of these groups represent. U1 group is for QED, right? That's the E and M fields and photon. Okay, these two together is just a single field, the electromagnetic field. I just written it because we call it like that, the electric and the magnetic field, or they're just EM fields put together. Okay. The next we have SU2. That is for the weak interactions. Okay, this was the Abdus, the Salam Weinberg. These were the scientists who worked extensively on this. I'll just call it the Salam Weinberg theory. It's also called electroweak interactions sometimes. It just depends on you what kind of lingo do you want to use. And the final we have is SU3, which stands for quantum chromodynamics. We talked about color of gluons, the RGB and so on. The SU3 corresponds to the study of quantum chromodynamics. And so yeah, that's about gauge theories. Now I'll just quickly tell you how these gauge theories look like. I'm assuming I have another 4 minutes left. Right, a lot of mathematics here, don't worry about it, but this is something that we know from beforehand. The theory of electromagnetism was developed by Maxwell back in 1800s or so, and he realized that his equations remain unchanged under certain transformations, which I've boxed with my red pen right here. Right, this is the vector potential. A is called the vector potential and phi is called the scalar potential. You don't have to worry about what they mean and everything, but Maxwell realized that back in 1800s, right, we're talking about pre-relativity era as well. Maxwell realized that his equations are invariant under these transformations. If you were to change your original scalar potential to some A prime, where what you've done is you've just added a gradient of some scalar field. And if you changed your scalar potential by subtracting the time derivative of the same scalar field, his equations remained unchanged. Right, back then he just didn't call it gauge transformations, but now we call them gauge transformations. Right, and the reason why we call them gauge transformations and all is a big story, but the result of that is whatever the new electric and magnetic fields that you get out of Maxwell's equations are the same as the original ones. They don't make a difference. Right, and that's when we realized that Maxwell's equations have a gauge symmetry. And which gauge group is this? It's the U1 gauge group. It's the U1 gauge group, right? And this is how we were able to tell that photon actually is a quanta of the electromagnetic field, right? It was by studying gauge electromagnetism as a gauge theory. Since we said gauge theory is a theory of fields, the field we are dealing with here is the electromagnetic field, or you may even call it the photon field if you would like to, right? And it's because of this U1 symmetry that we have a photon that is coming out. Right, so that's about electromagnetism. Now, I should warn you, the slides that I'm about to show you next might be very intimidating in terms of the symbols and everything used, but I assure you, you don't have to be worried about it. This is called a scalar field theory. It's more of a generalization of all the of the field theories like the Maxwell's relations and so on. This was worked out extensively by Paul Dirac. He gave out a scalar, he studied the scalar field theory, but in special what we're looking at here is the scalar orthogonal gauge theory. I won't be getting into the details of all of this, but one thing that you realize, it is from Noether's theorem, right? We invoke Noether's theorem again, and what we realize is because there is some invariance that is here, okay? So there is some invariance that is going on here, where G is some orthogonal matrix, there is a conserved current G. Okay. This is again assuming there are no interactions between the fields. That's when you have this. Okay. Right. But then Dirac realized there is some issues with all of this, so he modified it and he came up with a locally invariant gauge, locally invariant Lagrangian density, or Lagrangian, if you would. Right. Now, what this, sorry, just still here. This is the Lagrangian, that's just a derivative. Right. Now, what this is trying to tell us is how would your transformation locally affect the field that you're studying, right? Or in other sense, if you have an invariant field, what exactly is being conserved? It's the study of that, right? And there's a coupling constant G here. So that tells us how these things interact with each other. If I apply a transformation at one point, how does it affect the other? Some faraway point, like we discussed way back here, right? Here, right? If I was to apply a blue transformation T1 at L1, I hope you can see the screen because I feel my internet is a bit slow, right? So yeah, if I apply a blue transformation T1 on an L1, this green line here represents the coupling constant G, right? It's like communicator kind of a thing. In our different field theories, in electromagnetism, for example, this corresponds to the photon, right? The photon itself is massless, so it does not take energy to create them and so on. But that's studying gauge theories in a little more depth, which is our topic for tomorrow. And I think I will just show you one last Lagrangian. This is the Lagrangian for quantum electrodynamics, which we saw has a U1 gauge symmetry. Right. This part is the Dirac equation. Let me just put it as Dirac theory. Right. And this, you might have already realized, is from the field tensor, the electromagnetic field tensor. The people from Solstice, if you've attended my talks on relativistic electrodynamics, you would be familiar with the F mu nu notation. The rest all is just from Dirac's notation. Like I said, Dirac extensively worked in the field of gauge theories in general. And so he was able to formulate a Lagrangian for a quantum electrodynamic field. And with that, I conclude my talk. These were the references that I used for today, mostly mathematical physics, but they explained really well about what do these groups represent and so on and so forth. Thank you for your patience. I formally conclude my talk here. And if there's any questions, I'd be happy to answer them.
Yeah, Vikrant, I have one question. Is that if we consider the dark matter, does symmetry holds for this?
I'm not really sure because I haven't studied. I mean, as far as I understand, we still don't know what dark matter is made of. But if the particles called the axions and every particle that you hypothesize that dark matter is made of, I think you may apply some some kind of symmetry if it is possible. But as far as I know, I'm not really sure if we can apply to that as of now.
Okay, means if we come to know that in the dark matter there are some specific symmetries are there, then it might be that.
Sorry, your voice is breaking a little bit.
Yeah.
I think it's my internet.
Hello. Yeah. Hello. Hello.
Yes. Okay. Yeah.
You're
Now I
audible?
can hear you. Yeah.
Yeah. If my question is, if means if we know that dark matter is made up of something, then there might be that SU groups maybe increase. There might be possibility.
Possible. Yeah. That is possible. But I think we'll have to make a few assumptions for that. right? I mean, we'd have to understand what exactly would dark matter be made of if it is, correct or something. And we'd have to look at what kind of symmetries must it follow. Should it be a global symmetric theory? Should it be a locally symmetric theory? And what kind of coupling would it have, right? How would it affect stuff here and there? And again, that again, I think boils down to the question of how gravity behaves, because all these are gravitational interactions in the end. The way dark matter was through gravitational effects, right? The velocity of stars far away from the galaxy was not slowing down, but rather the same as the inner stars. So yeah, I think it does boil down to how gravity behaves at those scales and what particles is dark matter made up of. But I can't really give you a definitive answer for this. Sorry about that.
No, yeah. Okay, thank you.
Yeah.
You said the gauge bosons, we call it gauge bosons because gauge field can be quantized. So
Yes.
as a corollary, Higgs field can't be quantized.
Sorry, I can't. I didn't get that.
As a
The last one.
corollary, Higgs field can't be quantized because this is not Higgs boson. Higgs boson.
Yes. So the difference between a regular gauge theory and the Higgs field is that the Higgs field is a scalar field theory. You see back here, right? You see this expression on the screen, the scalar gauge theory, not the ON, but it roughly has the same form like this, right? So let me just write it down simply for you over here because I have a lot of empty space. I'll just put a line here. Oops, that's a bad thing. Right. So any scalar field theory, you have the Lagrangian density, you have some kinetic term, let's not worry about that, but you also have a potential term that depends on the field. Okay. Now, when you're, let's look at it in 3 dimensions. Okay. When you're this potential field, whatever you have is of the form like this, right? It's called a Mexican hat potential. If you've heard about this before, right? The Higgs field is somewhat here, right? And when you talk about Higgs boson, it's something that you observe over here. The Higgs boson is always observed over here. That this is what. So the Higgs boson is a part of SU2, the electroweak interactions and so on. And you might have heard something about the spontaneous symmetry breaking if you've heard about it. And in a sense, yes, you can say that the Higgs field is quantized and that's why you have the Higgs boson. But by that argument, it is a little difficult to tell why exactly should the Higgs boson have a mass, right? Because if I'm quantizing my electromagnetic field, I get a photon, which is massless. But if I'm quantizing my let's say the Z field or the W field, the Z bosons and the W bosons field, they have mass. The Z bosons, the the W bosons have mass. Right? It's around 80 to 90 giga electron volts. And the Higgs boson, which is also a result of a scalar potential, scalar field theory, also has mass. So there is something more going on rather than just quantizing it to get a Higgs boson. But yeah, in like a very general sense, you can call it to be that. You quantize your Higgs field and you get a Higgs.
And gravity will be in the gauge field. Gravity.
So yeah, general relativity can be called a gauge theory, but the problem comes at the Planck scale when you try to understand what's happening to gravity and space-time at a Planck scale. So for that, you'll have to study space-time symmetries in a little more detail. But as far as I remember, I think general relativity is a gauge theory. I'll just have to read up on that again, but I think it is.
Thank you.
But yeah, if you were to quantize your gravitational field, then you're supposedly supposed to, I mean, you should be getting a graviton, which is a particle
That's what I was
of gravity.
What I was aiming at. Thank you.
Sorry?
That's what I was aiming at because the graviton
Yeah.
is a quantized form, That's Thank you.
Right.
Thank you.
Yeah, we can.
Hey, go ahead.
Yeah. My question is, if we consider that a Higgs boson is means the quantized, okay, can we say that if Einstein's equation is equal to mc square, it is applicable to all that scenarios? But if we consider that is mc square is not true, okay, in the Higgs boson field, then this can be said that it is quantized. Means
I'm not
is-
quite sure I get your question.
yeah, means I'm saying that E is equal to mc square. We say that the mass energy equivalence. We say that we have that kind of energy, which is equivalent to mass, correct? So
Mm-hmm.
so
Yeah.
here, if Higgs boson, what the question is, the this boson should be have a heavy mass, correct?
Right.
Okay, so if it has a heavy mass, then it contains the energy, but its speed is zero.
Okay.
Yeah. So if we consider that E is equal to mc square is not true, okay, in that kind of dimension, then there might be possibility that we can actually identify what is the Higgs boson is.
Okay. Again,
Yeah,
so
I
so
know this is not a valid question actually. Just I think of
no,
it.
I
So
can't really comment about the validity of the question, but as far, I'll tell you what I understand about the relation between the Higgs boson and the equation of E equals mc squared. Right. I'll tell you what I've understood so far. I'm still studying about all of this, so I may
yeah,
not be able to give a satisfactory answer.
no, yeah,
But the Higgs field is it's an explanation, or it's like a solution to this effect that was observed called symmetry breaking. Like I just mentioned a few moments ago, there was some symmetry breaking that was observed, and that is why there was a need for something called the Higgs field that would explain this kind of symmetry breaking, and that's why this potential field has the shape that it has. It's called a sombrero potential or the Mexican hat potential. Okay, that's why in order to explain the symmetry breaking is why this potential was needed. Now the Higgs boson is, again, like I said, or like even you understood, it's a quantization of that, or a manifestation of that field. Okay. Now one thing is, all of these fields that you study, or that you hypothesize, or the field that you predict, are relativistically invariant. You have already incorporated relativity in them. Okay. And
okay,
if that happens in the very theory that you've constructed from relativistic assumptions, uh, any particle that you have will obey the Einstein relation. Okay. And in general, it's not just E equals mc squared, but they would rather follow this: E equals m0 c squared, m0 c squared c4 plus p squared c squared. They would rather follow the entire thing. That's the whole basis of Dirac's equation, right? And everything apart, that's like the first basis of quantum field theories and so on. They are relativistically satisfactory, right? I don't know if that answers your question, but this is what I have uh,
yeah,
understood of the relation between Higgs boson and the Einstein relation.
yeah. Means you mean to say that they are relativistically follows. Actually means the light, or we can say the velocity will be comparable to c. That's why E is equal to mc square is valid everywhere.
Yeah, so see, here we don't really talk about how fast the particles are moving when you're observing them, right? What we're more bothered about is how heavy they are or how much energy they carry, which are equivalent in a sense,
Hmm.
right? We really don't bother about, oh, the Higgs boson is moving at 1/10 the speed of light or equal to the speed of light and so on.
Yeah.
That's at least for our purposes here, that's not important. But what matters is that they still satisfy this relation,
Hmm.
right?
No,
That relation is more important to us rather than how fast they move in space and time.
no, I thought that if every particle gets a mass from the Higgs boson, so Higgs boson must be heavy. So that's why I thought that it is not
Okay,
moving
okay,
with the
okay.
speed.
No. Okay. Now I get your question. So
Yeah.
the Lagrangian for the Higgs boson, or the electroweak theory, has this kinetic term in it, right? And the process, and the way the Higgs field gives masses to the other particles is a little different. I think I'll try my best to discuss that tomorrow. Okay, I'll try to tell you briefly what exactly is this process of the Higgs field giving the other particles or the other fields masses. The Higgs boson doesn't give mass. It's the Higgs
Okay.
field that gives mass. The interaction of an
Okay.
electron with the Higgs field is what gives an electron its mass. Okay,
Okay. 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 Means
Higgs
Higgs
boson
boson.
doesn't.
Okay. Okay. Means it retains its mass.
Yeah, the mass of the Higgs boson is there. It may
Okay.
decay to something else, but the reason why other particles are said to obtain their mass from the Higgs field is because of their interaction with the Higgs field, not the boson.
Okay.
Now, if
Yeah,
you
yeah.
want to detect if there is a Higgs field, you need to detect a Higgs boson.
Okay.
The boson, the Higgs boson, is a proof that the field exists.
Yeah.
So to tell you.
Right. Okay. Okay. Yeah.
Okay, now I'm
Yeah.
glad
Yeah.
I could answer your question now.
Yeah. I got my answer. Yeah. Thanks a lot.
Yes. No problem.
Hello.
Yes. Hello.
Can you explain the last part of the previous slide again?
Which one? This one?
No, the previous slide.
The one on electromagnetism?
No, the scalar.
Or the scalar field theory. Actually, it's not that important, but all it's trying to say is that from you have a scalar field which is not interacting with each other or something, all right, and then whatever particle it has some mass m. You can write a Lagrangian for it, which has a kinetic term here. This is the T, and there is a potential term here, which is the V. Okay. Now this Lagrangian for a gauge theory, whatever gauge theory you put in, it has to be invariant under some gauge transformation, right? Like I said, you just put the word gauge in front of everything. So this so-called Lagrangian has to be invariant under that. And when we say invariant, we also imply that it's conserved. Okay, I hope I'm audible. My net seems to be acting a little glitchy.
Yeah, you're right.
Okay, I hope the screen is on the scalar gauge theory, because I don't know, it's different on my phone here. Is it on the scalar gauge?
Classical electromagnetic.
Yeah, okay. I think it's a problem with the internet. Let me just okay, I'm sharing my screen again.
Yeah, now it's on scalar.
Okay. But okay, I've stopped sharing. I don't know why you can still see it. Never mind. If you can see the screen there. Oh, I think it's the Wi-Fi of mine that is really slow. Yeah, it's the Wi-Fi that is slow. And I'm unable to share my screen right now. I think it's my internet problem. I'm really sorry. Yeah. Okay, never mind. So what I was telling you is, I'm sorry, what was your question again? I'm really sorry. I missed it. Oh, now you can see my screen. Perfect. Now you can see my screen. Can the person please repeat their question? I lost track because of this.
Yeah, can you explain the last part of this?
Okay. So until here, until this red line, right, the first 2 points talk about non-interacting Lagrangians or non-interacting fields. Okay, but these sort of relate to globally symmetric kind of theories. Okay, but a gauge theory has to be invariant under local transformations, right? So we have to modify our Lagrangian. So this was for global in a sense. Okay, but for a gauge theory, we need the Lagrangian to be invariant under local transformations. We want it to be the same for at every single point of the field. So we want to deal with local transformations. And that is why we change things a little bit. We change how we define our field, how we differentiate, and we change how we find the kinetic energy or the kinetic term for our Lagrangian and so on. Right? And using all of that fact, you can write a locally invariant Lagrangian. That's the last equation. Okay. The L loc, the fancy L LOC, is the locally invariant Lagrangian. Okay. And so in order to do this, you had to introduce a coupling constant that you can see here. Now, why was there a need of a coupling constant? We will discuss tomorrow when we're talking about gauge theories and Lagrangians more in depth. Okay, I still want to keep something left for tomorrow. So yeah, if you don't mind. But in brief, yeah, the last part deals with how do you get a locally invariant Lagrangian by changing how you define your fields, how you define your derivatives, and introduce some sort of coupling between them so you can understand what's going on at different points of the field. I hope that answers your question.
Yeah. Yes.
I think there were a few questions on chat.
Okay, let me check that out. Why Hermitian and traceless? Are they showing some property of the complex space? Good question. The answer, I don't know. I don't think there is any specific reason. I mean, if there's any specific property of complex space that we're trying to represent, but I think it's just a condition that we got from mathematical working out. But I'm not sure. I'll probably check it out if there's any relation between if there's any relation between a Hermitian and traceless operator with the complex space that we have. And if I find something, I will get back to you on Discord. Okay, Dinesh asks, in GR, there is transverse and traceless gauge, which is, I'm not sure I understand that question. Dinesh, do you mind asking your question again? In GR, there is transverse and traceless gauge, which is different from this gauge theory. I'm not sure I understand that. Really.
So in GR, we study about transverse and traceless gauge, TT gauge, so which is related to this sort of gauge theory that only I wanted to ask.
Okay. Okay. I think my internet is really slow. So, all right. So I haven't really read about transverse traceless gauge much, but I think that has to do with more. That has to do more with how gravitational waves work, and the reason. I mean, how I'm guessing that is because your gravitational waves have a quadrupolar moment. But I think these are not related. Because the kind of theory that you study for gravitational waves is linearized gravity, right? That's where you apply perturbation theory to gravity, and you have a metric tensor that tells you about the geometry of space-time and so on. So it's more related to the theory of gravitational waves and not about maybe not much about um, you know the gauges that we are trying to talk about. But I think there might exist a relation, maybe some sort of weak force relation or some relation like that, because gravity is an inverse squared law. Um, but yeah, you can classify that one as a gauge theory. But what I am not sure about if the gauge theory that we talked about here is the same as that one. That is a gauge theory, yes, right? There is a gauge symmetry and so on, but I'm just not sure if it's the same that we discussed today. I'll probably read up on that and get back to you.
Okay, all right. Thanks.
I hope you're on Discord, right? You can join our Discord server, the virtual campus or the Solstice group. Are you a part of Solstice Summer Project?
Yes.
Okay, then cool. Then you can just tag me on any one of the channels and just ask a question again so that I don't forget. And yeah, I'll get back to you as soon as I can.
Okay, all right. Thanks.
Thank you. Anshul says very good and simple explanation. Thank you, Anshul, for that. And if there's no more questions, then I think we can successfully end the talk here and stop the live streaming as well. Jeevan,
Yeah,
if you heard,
Vikrant, can you stay for a bit longer?
Yeah, Sagar, sure, no problem. I think you can stop the live streaming though.
Yep.
Yeah. Thank you everyone for attending. Really appreciate the patience.
Thank you.
Thank you.
Thank you. I'll see you tomorrow. I'm going to stop sharing my screen now.